So, first problem says posted, and will be due a week from today in class. I didn't receive many responses. I have received one response about availability. So let's talk about it. Tuesday, I think, is the best day for office hours. I'm suggesting 2 o'clock. Okay. So that's what we'll do, and I'll find a week. There's a couple of different related administrative issues. A suggestion came up of, boy, wouldn't it be better to have this class 2 days a week rather than 3 and do it for longer, which would be my preference as well. Part of the issue is room availability, and the other is, well, your availability. In addition, although I don't think I'm traveling very much this semester, I'm traveling some, so it's good for us to think about alternative makeup times for lecture. So my first question is, if we were to extend this class for 20 minutes on either side, are people have class before this class? So if we could start this class at whatever, a quarter to 22, that's about, or what about after this class?
And the benefit would be no class on Friday then.
There's lots of benefits. You only have to deal with me twice a week, that's a benefit. I only have to prepare lecture twice a week. Yeah. All right, we'll think about that. That would be my preference. Great. All right. So let's see. Does anybody have any questions of any kind, administrative or otherwise? All right. So last time we were just getting into it, and we did our motivation, and we were talking firstly about the extreme importance of the first look at any physics problem is to understand the scales of interest. And those scales, characteristic scales, are set by the characteristic constants of the problem, the physical constants. So in an experimental setting, they might be set by the geometry, right? I mean, if you have coils that are making magnetic fields, you know what the radius of that coil is, it can tell you something about the characteristic fields that and so forth. But if we just think about fundamental constants, that gives us some sense. The first thing we should do is make characteristic lengths and energy and so forth out of our constants. And that is what in the biz is called atomic units. Okay? So quite often, the serious atomic physicists, of which I am not myself, I only play one on TV, there's the camera to prove it. We'll express everything in atomic units. Okay, so the characteristic length scale that we get out of these characteristic constants of the electron in quantum mechanics is the Bohr radius, and the energy is what we call the Hartree. So what we talked about the general hydrogenic problem, which corresponds to the interaction, typically binding of two oppositely charged particles regardless of their mass, regardless of their charge. And that could be things like muonium or positronium. But for the moment, we're going to restrict our attention to the problem of thinking about normal matter, where we have a nucleus with some number of nucleons, some number of protons of atomic number Z, and 1 electron. Okay, so it's hydrogen plus. I mean plus, meaning that plus lots of other stuff could be, 81 times ionized lead. Okay, it's the same problem. As far as the Coulomb problem goes. So we're just looking for the energy levels, the bound states. We're reviewing the very elementary problem of the hydrogen atom. We express our Hamiltonian in terms of radial and angular kinetic energy and the Coulomb potential energy, and we're looking for the bound states. So E sub B here is the binding energy with the negative sign explicitly expressed. As you know, we can solve this problem exactly, and one of the reasons we can do it is by taking advantage of thinking about the symmetries. This is the hydrogen problem is an example, of course, of the standard, one of the most important problem in physics, the central force problem, in which the potential is spherically symmetric. And in the context of quantum mechanics, that means we have a complete set of commuting operators that fully specify the eigenstates of the Hamiltonian. Okay? So the Hamiltonian, the magnitude of the angular momentum, and any one component specify three commuting operators. That is a complete set because we're talking about 3 degrees of freedom once we fix the nucleus. Okay, so this is classical mechanics as well. And in quantum mechanics, what that means is that we can separate coordinates and express the eigenstates of the Hamiltonian in the position representation separated into a radial wave function and spherical harmonic. The radial wave function, as we discussed last time, is conveniently written in terms of the reduced radial wave function with the 1 over r explicitly factored out. And thus, when plugged into the 3D Schrodinger equation and separated, we get the familiar but incorrectly written, but now corrected, one-dimensional Schrodinger equation, the reduced radial equation. All right. So, firstly, to remind you of some things, the first thing we know is the existence of the symmetry is intimately related to the fact that the energy levels have degeneracy. So, that's a fundamental principle that we can see. And in particular, if we have a continuous symmetry, a symmetry that generates a continuous group, well then we are assured to have some degeneracy. And what is that degeneracy in this case? Well, that degeneracy, in this case, we have spherical symmetry. That's one of the symmetries we have. This potential only depends on the distance from the origin and not the direction of the electron relative to some fixed coordinate system. So that tells us that, for example, if I look at one of the eigenstates of the Hamiltonian. Now let me explicitly, before I do that, I wrote down 2 of the quantum numbers. Of course, these are the eigenvalues associated with L squared and the eigenvalue associated with LZ in the usual way. We're looking for bound states, and therefore we'll have discrete eigenstates, discrete eigenvalues, I should say, of the Schrodinger equation. There are, of course, a continuum also associated with the unbound states of the electron, and they're essential in thinking about the scattering problem, which we will ignore. But for the moment, we're thinking about the structure. And to remind you, so there is, of course, another quantum number here, which has to do with the number of nodes in the wave function, right? because this is a 1D type Schrodinger equation. Each time you have another node, you have a new eigenvector. So that is, I'll call that n sub r, which is the radial quantum number. Okay? Now, of course, as we know, the potential here, there is a effective potential which involves the potential plus the angular momentum barrier. And so our radial wave functions will generally also depend on L. Because for different values of L, we have different effective potentials. Okay? So let's suppose we have one of the eigenstates of the system, which is denoted for the moment by these three quantum numbers. The radial quantum number, the L and the M. This is not the principal quantum number. We'll come back to remind ourselves about the principal quantum number and its relationship to these other quantum numbers. So generally speaking, we're looking at the eigenstates, the binding energies, which are going to depend well, just forget about the negative sign and just say there's some energy eigenvalue which in general will depend on all these quantum numbers. But of course it doesn't depend on all these quantum numbers, and one thing we see from the symmetry initially is that, for example, if I look at a rotation of one of these eigenvectors and rotate it around any axis, well, let's do that. Let's say I rotate it around the x-axis by some arbitrary angle, theta. So that, you'll recall, is the rotation operator. And if I take this and I apply it to one of the states, I can ask, is this still an energy eigenvalue, an eigenstate? And the answer is, of course, yes, because not only does H commute with Lz, but H commutes with Lx, H commutes with Ly. Even though Ly and Lx and Lz don't commute, this is spherically symmetric. Doesn't matter what axis I choose, and the Hamiltonian is invariant. So if I apply my Hamiltonian to this, well, that is equivalent since H commutes with Lx, it commutes with the rotation operator, right? It doesn't matter how many powers. And so I can write this as the rotation operator acting on H, acting on the state, and this is E sub n r Ln. However, we know how the rotation operator acts on a state. First of all, a rotation operator doesn't change the magnitude of the angular momentum. It only changes the direction of the angular momentum, and only acts on this part of the space. So this could be written in general in terms of a complete sum from minus L to L, because of course M goes from minus L to L in unit steps, acting C sub n prime and R L n prime. And H is a linear operator, can move through this sum, in which case I get sum over n prime, C sub n prime, E sub n sub R, L n prime, times the states. And since these have to equal one another, and this is true for an arbitrary theta, the only way that could be possible is if the energy eigenvalue is independent of n. Is that clear? Do you buy that? this has to be able to be factored out of the sum in such a way that at the end of the day, oh, this is terrible, that equals this. Okay, so I'm just reviewing something that I'm sure you know, that if I have a spherically symmetric potential, a situation in the physics independent of direction in space, then the energies are independent of the m eigenvalue. I need the m eigenvalue in order to specify which eigenstate it is, but they are degenerate. So one thing we have from spherical symmetry here is that we have the energy is independent of the m quantum number. So that means we have, for a given L, 2L plus 1 fold degeneracy for a central force problem. Alrighty. So, so now we want to just review quickly the solutions to the radial wave equation. So again, we're looking at the problem on the half line. So R here is the magnitude of the distance of the electron from the nucleus. So it only goes from 0 to infinity. We have the Coulomb potential, 1 over R. We have generally, for an arbitrary L different from 0, we have the angular momentum barrier and together they give us some kind of effective potential that depends on L. And then we solve for the bound states inside that effective potential. All right, elementary quantum mechanics, wave mechanics. Let's see, what do I want to say? Well, the first thing I guess I want to, I guess the next thing I want to say here is, if we're going to solve this differential equation, the first thing we should do is get rid of the units, right? So we've already done that, kind of. But things are a little bit, we have this z in here, which we didn't have when we considered characteristic atomic units. So although z has no dimensions, it's a number we kind of like to get rid of and think about how things scale when we have different size nuclei. So we can kind of do the same trick here about thinking about the characteristic units. So we want to make dimensionless. So we have the same, we'll use the same trick that we used on Monday and think about, we're going to have to think about a characteristic length and a characteristic momentum. which would just be given by that, and a characteristic energy. Now we have both potential and kinetic, and we just get a characteristic scale of them, we set them equal. So our characteristic energy is the characteristic kinetic energy, p squared over m, and that we set equal to the characteristic potential energy, which is z e squared over a naught, right? That's looking at this potential energy and just setting r being equal to the characteristic length. So from this, we see that the characteristic length is h bar squared over m e squared times z. No, is that right? Over z. Okay, so this is equal to the Bohr radius divided by the atomic number. So the bigger the atomic number, the characteristic scale, the characteristic energy scales like 1 over z, the characteristic length, excuse me. The characteristic energy therefore scales like z squared times the Hartree. Okay, so that's one thing we learned from this. So given that, we let us re-express our radial equation in terms of dimensionless units. So we're going to take out the dimensions, take out the units, and define a dimensionless length x as r over the characteristic length, and the characteristic and the energy or the binding energy will be scaling out the characteristic energy. So with that, our radial equation becomes the following. Okay, so that's the Diffie-Q that we need to solve in order to determine the binding energy of hydrogenic atoms. So to do that, we just again remind ourselves of what determines the eigenvalues is the boundary conditions. Okay, so although r here is written as a coordinate on the half line, really r is the magnitude of the square root of x squared plus y squared plus z squared, which means that at the origin, it can't blow up at r equals 0. Right? Otherwise, we wouldn't have a smooth differential equation as a function of x, y, and z. So there's a kind of hard wall boundary, well, not quite hard wall, but that depends on I should go back and say it depends on L. What happened to my L? Good point. I did it again. L and L plus 1. Should be there. So the boundary conditions. So as x goes to 0, u doesn't blow up. So from this differential equation, if we go to the origin, this thing starts to dominate over this. And the differential equation then tells us that u has to go like x to the L plus 1. because then I take the derivative there. Yep. So, to remind you quickly, if we look at this, for example, remember the actual radial wave function. I mean, this will solve this differential equation when this is 0. What we learned from this is that the actual radial wave function scales like r to the L. Which means that for all L different from 0, the radial wave function, and therefore the wave function, goes to 0 at the origin. There's a node in the wave function at the origin, which is why I say for everything other than L equals 0, it's as though there were a hard wall at the origin. For L equals 0, it's constant, which means that there can be a large probability amplitude for the electron to be at the origin if the orbital angular momentum of the electron relative to the nucleus is 0, because then it has 0 impact parameter. So it's going to spend a lot of time at the nucleus. The other boundary condition is as x goes to infinity. As x goes to infinity, the effective potential goes to 0. And therefore, we end up with the differential equation in that regime, in the asymptotic regime, when x goes to infinity. So that's an equation we can solve in this asymptotic regime. What's the solution? Hint, it's not the harmonic oscillator. Well, it looks like it. Close to the harmonic oscillator. Please tell me the solution to this equation. At least one possible solution. Yeah, so sinh and cosh, that's definitely a solution to this. Or e to the exponential, e to the plus and e to the minus of the square root of this constant. Now we have this another boundary condition, which is that u has to go to 0 at infinity, right? So that tells us that in this asymptotic region, u of x goes like e to the minus the square root of 2 epsilon times x. Okay, satisfying the boundary conditions. So we can put all that together. And we learn that we can write down an Ansatz, everyone's favorite German word next to eigenvalue. At least it's one of my favorite German words. Which is puts explicitly in the behavior of the radial wave function in the asymptotic regimes, and then just leave everything else put into this function, which has to be a polynomial. It has to be in order to satisfy these conditions. If it blew up or is exponential some way, then it wouldn't have these conditions. And it also has a polynomial that has certain behavior as x approaches 0. So now we plug all that in, and we get the following. where prime is derivative with respect to its argument. Okay? And that is an example of a hydrogenic equation. And the solutions which satisfy the boundary conditions therefore put restrictions on the eigenvalues. You may have done this in the past, you put in the polynomial, you get the recurrence relations, and then you show that it chops off, and blah, blah, blah. The point is, we know the solution to this equation. And so the solution, satisfying boundary condition, make us that there are only this allowed values of the quantum numbers must satisfy the following. The number of radial nodes equals 1 over the square root of twice the binding energy minus L minus 1. And thus, we end up with where this is n sub r can be none, it's a non-negative integer. L, of course, can also be 0, 1, 2, 3, etc. And so we get the equation for the binding energy, which depends on n sub r and L as equal to 1 over 2 n sub r plus L plus 1 squared. The solution to the hydrogen atom, or hydrogenic atom. Now, we see here something that is particular to the 1 over r potential. And in particular, what we see is the energy does not depend independently on n sub r and L. It depends on the sum of them. So there is an additional degeneracy. In fact, one typically will define this sum as n, which is known as the principal quantum number. And then what we say here is, so here the principal quantum number, because n sub r and L run from 0 to infinity in integer units, the principal quantum number run from 1 to infinity. So n equals 1 is the ground state, okay, as the biggest rounding. So the principal quantum number goes 1, 2, 3, etc. And for a given, so let's write all this thing down. So the bound states of hydrogenic energy then we have solved depend only on one quantum number, the principal quantum number, so we need the characteristic scale divided by 2n squared, because I'm going to put that into units. And the characteristic energy we said was z squared times the Hartree. the Hartree is E squared over A naught, 2n. And that is equal to minus Z squared over n, E squared over 2A naught, which is the Rydberg. .6 EB approximately.
Is it n squared all the way through?
It is, sorry. Indeed it is. Okay. So, and where n is 1, 2, 3, etc. Okay, now of course, the eigenstates of the system, the energy eigenstates are specified by 3 quantum numbers, right? Of course, from this, what we see is n sub r is equal to n minus L minus 1, right? So L for a given n L goes up to from 0, 1 all the way up to n minus 1 are possible values of L. And n is between minus L and L in integral units. So what we see here is for the case for 1 over r potential, we have another degeneracy. Right? Because the energy eigenvalue not only is independent of m, which we knew from the get-go because it was spherically symmetric, but we certainly did not know from the get-go that it was independent of L. In fact, any other potential that is spherically symmetric, like a particle in a spherical box, or partial waves, or a 1 over r squared, generally will not be independent of L. They will depend strongly on L. So we'll come back to this. Why in the world is this, what is this telling us about symmetry, or is it an accident? Sometimes this is known as an accidental degeneracy, but it's no accident at all. We have another degeneracy, so we have these states, and so the total degeneracy for a given principal quantum number n is the sum L goes from 0 to n minus 1, m goes from minus L to L. Well, let's put it this way, there are 2L plus 1 for a given value, and this is equal to n squared. Okay? So that's the total degeneracy of these things. And so the energy levels of hydrogen have a very particular form that is unique to hydrogen and hydrogenic atoms. It is not true of helium. It is not true of sodium that we have this kind of degeneracy in L. Not at all. Not even close. Not even close to degenerate, and we'll come to that in a moment. Well, maybe not in a moment, but at some point in the class. So just to quickly remind you, if I draw the energy diagram, if this is the ionization level, 0, then we have the ground state, n equals 1. So let's call the energy, let's see how I sketched it out. I don't know if I did it in Rydberg's. Yeah, that's right, I did it in Rydberg's. So hydrogen, let's do. So here's this is a half, here's a quarter. So we have an energy level here, we have an energy level here, and then we have a 9th. For n equals 3, we have an energy level here, we have an energy level here. Actually, each one of these is multiply degenerate. So I'm writing this here, and the way you'll see these kinds of spectra drawn is by looking at a series with a given L. So to remind you of spectroscopic notation, one of the most arcane Sanskrit-like things, even worse than CGS units, but you know, you gotta live with it, is so we denote an orbital with the principal quantum number and the angular momentum quantum number. And of course, we denote, to confuse everybody, L equals 0 as S, L equals 1 as P, L equals 2 as D, L equals 3 as F, and then G, H, I, J, K, L, M, N, O, P. I don't know if there's a QRS or a TEV, but it could be. So why in the world? Well, we had sharp, principal, diffuse, fine. That's what these things meant in terms of what the lines look like on the spectrometers. But that's what we're stuck with. So the ground state is the 1s state of hydrogen. The first excited state has multiple degeneracies, right? Because n equals 2, there are 4 levels. One of them is the 2s, and 3 of them is the 2p. And then we go up to 3s, 3p, 3d, etc., etc. And of course, they bunch up very quickly when you start getting up into the higher excited states. What else do I want to say? Oh yes, the energy eigen states that wave functions. So the polynomial f that we described earlier is an example of a hypergeometric function, and that hypergeometric function has a particular name. It's the associated Laguerre polynomial, which is one of many, 19th century polynomials. Good old Laguerre. He was not Lapisse, he was Laguerre. So there's some constant here, n sub r, 2 over n. That's n sub r, that's n x. So the number of radial nodes determines this the order of the Laguerre polynomial, and this is his associate. All right, so with that, we can write down the energy eigenfunctions. For a given principal quantum number L and M, we have the radial wave function putting in everything. There's some normalization constant that depends on L and N. We have the factor x to the L, which is in putting all the units back. This was the characteristic length scale. Then we have that exponential fall off at far distances. That's the square root of epsilon stuff that we had before. And then we have the polynomial, which if I write out in terms of that, 2z over n, r over the Bohr radius times y ln theta and phi. Okay, I want to conclude this lecture by telling you something maybe you don't know. You probably know all of this. I hope you do. At some level, maybe it's in the depths of somewhere in the back of lobe 3 of the brain, but you know, you can dig it out. But the question is, why, for a 1 over r potential, do we have this degeneracy? Well, it's because there is another conserved quantity in the problem that was discovered or pointed out or realized by Laplace, but he got screwed because he has enough stuff named after him. It's called the Lenz-Runge vector. So, if I have a central potential and no momentum is conserved, and if I were to look at the trajectory, classical trajectory, what I would generally find if this was the center, where the central force is coming from, and it's a particle moving in an attractive central force, its trajectory would generally look something like this. You guys are probably too young to remember spirograph. Maybe
It's hard to get through the
is it on an app now somewhere? But anyway, Google spirograph. It was a cool toy for people like me. The trajectory will generally look like this. It won't close, and it'll eventually make a dense kind of covering of a two-dimensional surface. Okay? And if I were to think about this not in configuration space, but in phase space, it would cover a torus, and it would uniformly, ultimately cover densely the torus. So that at any time, give me a delta, I'll give you an epsilon, it'll get there close enough to some point on the torus. So this is for an arbitrary V of r. But for have a 1 over r potential, we know what the trajectory is. It's the famous Kepler orbit. It's an ellipse. So this means that if I were to think about the vector that kind of points from the point to the, I don't know, is it the perihelion or whatever helion, it's constant. And that vector is called the Lenz-Runge, sometimes Laplace vector, is fixed. And that vector is defined classically as 1 over, if I have, so I have, let's just call this kappa, whether it's gravitational potential or Coulomb potential. this is conserved. If you were to take the time derivative of this vector in the presence of this potential, you would find that this is constant. Okay? Now, that has implications for quantum mechanics, because conserved quantities are related to symmetries. Now, quantum mechanically, one can define a quantum length Runge vector by symmetrizing, because of course L and P don't commute quantum mechanically, so I need to symmetrize the cross product. Turns out that this commutes with the Hamiltonian. All components of it. Of course, all the components don't commute with one another, but they do commute with the Hamiltonian. So there is something going on here. And actually interesting, so I was just reading about this in the last week. I didn't know this was all kind of reanalyzed again in the 1930s by Fock. And this is intimately related to what's called SO4 symmetry. Now that's, I think, is pretty cool, so let me just quickly outline this. What is SO4 symmetry? Well, what's SO3 symmetry? SO3 symmetry is the symmetry of rotations in 3 dimensions that preserve the inner product of 2 vectors in 3 dimensions, right? So it's a rotation in 3D. Clearly, this has SO3 symmetry because angular momentum is conserved. But it turns out that because it's not just, SO3, the generators of SO3, or the quantum mechanical equivalents, are, this defines this is just a little bit of an advanced chatter for the moment, just to give you just a little bit of a basic. We know that the components of angular momentum define the Lie algebra that generates the group associated, at least in classical physics, with rotations in the tree, and then in quantum mechanics slightly differently. But it turns out that there's another set of commuting operators like this, and let me just quickly write them down. And I'll post stuff on the website for those who are interested. So it turns out, let me define a tilde, the I component of this, as the square root of n divided by twice the energy, or the binding energy, times what I call A over there. And then define 2 new vectors whose components, the vectors T and S, have components which are symmetrized versions of the orbital angular momentum and this lens Runge vector. It turns out that you can prove the following. H commutes with T, and H commutes with all components of S. T squared equals S squared. All of the components of T commute with all the components of S. And each T and S form a copy of the Lie algebra SU2, which in classical physics would be little SO3, or SO2, excuse me. So the commutation relations I'm writing down are the familiar commutation relations for angular momentum, right? They look like the commutators for angular momentum. So they generate two copies of the rotation group in 3 dimensions. And it turns out if you have two copies of the rotation group in 3 dimensions, that's equivalent to the rotation group in 4 dimensions. So SO4 is isomorphic to SO2 copied with SO2. So all this gibberish, let me reduce it to the following statement. It turns out that there is a one-to-one mapping between the 1 over r potential in 3 dimensions and free particle motion for a sphere in 4 dimensions. That is to say, if I had, this is equivalent to free particle constrained to the 3 sphere. So let's suppose I had Euclidean 4-dimensional space. And embedded in that Euclidean 4-dimensional space, there was a sphere. That is the sphere S3. That is the set of points with constant x squared plus y squared plus z squared plus w squared. And then I just let a particle undergo geodesic motion on that sphere. And I did a mapping of that 3-dimensional sphere, onto 3-dimensional Euclidean space. I would get this. So there is this 1 over r potential is intimately related to the fact that there's not just one copy of a rotation group, but there's 2 copies of a rotation group. There is a special geometry, there's a special symmetry associated with that, and that gives rise to that spectrum that we saw. Or at least that's one way to understand why the different L's, even though we have a different effective potential for different L's, nonetheless, the energy levels are the same and degenerate. I think that's pretty cool. I knew about SO4 symmetry, but I never knew that a Keplerian orbit is isomorphic to free particle motion on the 3 sphere. I think that's pretty neat. Yeah. All right, gang. We'll pick it up next time.